Imagine money that can hold itself, check a rule, and move only when that rule is satisfied. That is the basic promise of a smart contract. Not magic, not a lawyer in your wallet, but code that runs on a blockchain. The name can be misleading. A smart contract is usually not a legal contract written in code. It is a computer program. It can support an agreement, automate a payment, or enforce a rule. But the blockchain does not understand fairness, intention, or context. A smart contract is a program stored on a blockchain. People interact with it by sending transactions. When it receives a valid transaction, it runs the logic inside the program and updates the blockchain state according to the rules written in its code. On a normal app, the company running the server can change the database, pause accounts, or edit the rules behind the scenes. On a public blockchain, the contract code and its activity can often be inspected by anyone, and the network agrees on the same result. A classic analogy is a vending machine. You put in money, choose a snack, and the machine releases it if the conditions are met. A smart contract is similar, except the machine lives on a blockchain and may control tokens, digital items, or permissions. At the simplest level, smart contracts follow if this, then that logic. If the buyer pays the correct amount, then release the digital item. If the deadline passes, then refund the deposit. The power comes from making these rules public and automatically executable. On many blockchains, a smart contract has an address, just like a wallet has an address. But unlike a wallet controlled by a private key, a contract is controlled by its code. People send transactions to that address to call specific functions. A contract has functions and state. Functions are actions the contract can perform, like deposit, withdraw, vote, or transfer. State is the information it remembers, like balances, owners, prices, votes, or whether a deadline is already passed. Picture a simple escrow. A buyer sends payment into a contract. The seller sends the item outside the blockchain. When the buyer confirms delivery, the contract releases the payment. If no confirmation happens by a deadline, the rules might allow a refund or dispute process. This example shows both the strength and the limitation. The contract can hold and release funds without a traditional middleman, but it cannot magically know whether a physical package arrived. For real-world facts, it needs some trusted input from outside the chain. An oracle is a service that brings outside information to a blockchain. That information could be a market price, a sports result, a weather reading, or a proof that an event happened. Oracles are useful, but they also become part of the trust and security model. On-chain means the data and execution happen directly on the blockchain. Off-chain means something happens elsewhere, like a website, sensor, server, or human decision. Many real applications combine both. The key question is always what the contract can verify by itself. If this kind of technology explanation helps you, consider subscribing. We keep the focus on clear mental models, not hype. Now let's go one level deeper and look at what actually happens when someone uses a smart contract. When you use a smart contract app, your wallet prepares a transaction. You review what you are about to approve, then sign it with your private key. The transaction is sent to the network where validators include it in a block if it is valid. Running code on a blockchain is not free. Users usually pay a fee for computation and storage. On Ethereum and similar networks, this is often called gas. Fees discourage spam and compensate the network for processing the transaction. A blockchain needs every validating computer to reach the same answer. That means smart contract execution must be deterministic. If the same transaction runs against the same state, every honest node should calculate the same result. This is why random web requests cannot be used directly. A smart contract does not usually wake itself up just because time passed. It runs when a transaction calls it. If a payment needs to happen every Friday, some account or automation service must trigger the function. The contract can then check whether the timing rule is satisfied. This is where on-chain automation comes in. Automation networks, bots, or scheduled keepers can monitor conditions and call contract functions when needed. They do not change the rules. They act like messengers that say, "Now is the time to run this function." Automatic payouts are one of the easiest use cases to understand. A contract can split revenue among creators, send rewards to participants, or release tokens after a waiting period. Once the conditions are encoded and funded, the payout logic can execute consistently. Many tokens are also smart contracts. The contract keeps track of who owns how much, how transfers work, and whether any special permissions exist. When you send a token, you are often asking a contract to update its internal record of balances. NFTs use a similar idea. The contract records which wallet owns a particular token identifier. The image, ticket, game item, or membership benefit may be connected to that record. The smart contract does not make the item valuable by itself. It provides a shared ownership record. One reason developers care about smart contracts is composability. A contract can interact with another contract the way software tools can plug into each other. A lending app, exchange, wallet, and token contract can become building blocks for more complex applications. This building block quality can speed up innovation. Instead of rebuilding every feature from scratch, developers can connect to existing contracts. But it also creates shared risk. If one important building block has a flaw, many apps depending on it may be affected. People often say smart contracts are immutable. In practice, many contracts are hard to change after deployment, while some are designed with upgrade mechanisms. Immutability can protect users from hidden rule changes, but it also means mistakes can be difficult or impossible to fix. Some projects use admin keys or upgradable designs so bugs can be patched. This can be helpful, but it introduces trust. If a small group can upgrade the contract, users must trust that group not to abuse the power, lose the keys, or make a bad change. A normal software bug might crash an app. A smart contract bug can move real assets. If the code allows a withdrawal twice, calculates a balance incorrectly, or forgets to check permission, an attacker may use the contract exactly as written to drain value. One famous class of bug is reentrancy. In plain English, a contract sends funds to another contract before it finishes updating its own records. The receiving contract calls back again, and the first contract may repeat the payment because its balance record has not changed yet. Another common problem is weak access control. Some functions should only be available to an owner, a governance system, or a specific contract. If the code forgets to check who is calling, a stranger might mint tokens, change settings, or withdraw funds. Data can also be attacked. If a contract depends on an outside price and that price can be manipulated, the contract may make the wrong decision. A smart contract is only as reliable as the code, the data inputs, and the assumptions behind them. Security audits, testing, bug bounties, and formal verification can reduce risk. They do not eliminate it. An audit is a careful review, not a magic shield. Users should understand that smart contracts can be transparent and still contain mistakes that are hard to notice. Users also face risks outside the contract itself. A wallet may ask you to approve a token spend. If you approve too much to a malicious or compromised contract, it may later transfer tokens you did not expect. Signing is powerful, so every approval deserves attention. This is why the word smart can be dangerous. The contract follows instructions, but it does not judge whether the outcome is reasonable. If the code says release the funds, it releases the funds. If the code has a loophole, the blockchain may faithfully execute the loophole. Smart contracts are strongest when the rules are clear, the assets are digital, and the needed data is already on-chain or reliably supplied. Token transfers, escrow for digital goods, transparent voting records, automated payouts, and decentralized finance all fit this pattern in different ways. They struggle when the situation requires human judgment, private information, legal interpretation, or messy real-world facts. A court can consider intent and context. A smart contract cannot. It can only process the inputs it receives and the logic it was given. The best mental model is not a robot lawyer. It is a shared rule machine. Anyone can inspect the machine, send it valid inputs, and see the results recorded on a shared ledger. That makes it powerful, but also unforgiving when the design is wrong. Smart contracts matter because they turn some kinds of trust into software and shared verification. They can reduce middlemen, automate value, and create open building blocks. But they also move risk into code, data, keys, and design choices that users need to understand. If you still have questions about smart contracts, leave them in the comments. Ask about escrow, token approvals, oracles, gas, exploits, or anything that felt unclear. And if you want the next explainer to cover a specific crypto or AI topic, suggest it below.